Mecharithm family. I hope you're doing great and you're ready for another episode of Robotics Centered Meetings. I will be talking today with Ardalan, a Ph.D. student at Carnegie Mellon University and a former robotics software engineer who has recently published a series of posts on LinkedIn on how to become a robotics engineer. In response to the robotics community's high praise, he decided to combine these posts into a nice article for easier and permanent access. He's here today to discuss these posts and his article and to help you to become a better robotics engineer.
Hi, Madi.
Hi, Ardalan. How are you doing today?
Good. How are you? Good to see you.
Pretty good. Thank you so much. Thanks for being here. We are happy
absolutely. My pleasure
to have you here. How are you doing today? How's everything in Carnegie Mellon?
Great. It's snowing pretty heavily today, so everyone is going to be working remotely for a little bit. You can't even get out in the street, so yeah, it's pretty.
It's freezing out in here, Austin, as well.
Oh wow, yeah. I thought it would be warm there.
No, it's freezing here. Winter is coming, I guess.
Yeah.
That's a nice dog, robot dog, by the way, in the background.
Oh, yeah.
I, along with the rest of the Mecharithm fam, would like to know more about you, your background, the robotics projects you've worked on, and what you're currently working on.
Yeah, absolutely. So I guess I'll start with undergrad. So I did my undergrad at UIUC, University of Illinois at Urbana-Champaign. And I did it in mechanical engineering. And so I was actually completely interested in, was like completely into aerodynamics and fluid mechanics for the first 2.5 years. And I never really had much of an exposure to like what it would mean to be in robotics. I did have some experience, building circuitry during high school, but I never thought that it would be applicable in a different type of way. So around the third year of my undergrad, I took a class in industrial controls and mechatronics, and got very interested in it. And since then, it's been just, I've been basically hooked. So at the end of my third year, I worked on a project on an autonomous land sailor. It was basically like a 3-wheeled vehicle that would propel with wind. And it had like a little flap on it that would automatically adjust the angle of attack with respect to the wind direction. And so that I almost worked on it for a year. And by the end, I was able to like show it tracking a reference with just wind power and steering, which was pretty interesting. It was both like hands-on building the robot as well as, writing the control and all that for it. And then, yeah, basically the last 2 years, I really just honed in on mechatronics, robotics classes, took every single control system class that the university offered. And then I did an internship at, I think now it's called Virgin Hyperloop One. Back in the time, it was a startup of like 200 people. So over there, I worked on dynamic simulation of the pod moving through a tube at very high velocities, and like what it would mean for it to, get perturbed a little bit. Like if something is traveling at 500, 400 miles an hour, even a little bit of perturbation can cause a drastic dynamic change. So was working on that. And then after that, I started full time at iRobot, worked mostly on automating the robot testing. Right now, a lot of companies, even today, they have sort of a manual testing procedure for their robot. So they build a robot, but then everything after that is kind of a manual process. So I worked on basically building sort of an assembly line of robot testing with a robot arm. So like a series of robot arms, robots come in after manufacturing and you perform a bunch of functionality tests, like hit the bumper of a Roomba or, press a certain button, automating all these different tasks that you need to do all the checks on the robot. And then so I was there for a year, and towards the end, I felt that I want to get more into the algorithm side, and get a more of an advanced understanding. So that was the time that I applied for CMU, and then I got in. I started working in the robomechanics lab with Professor Aaron Johnson, who is also currently my advisor, on legged robots. So it's really big on legged locomotion and control, estimation, motion planning, all different aspects of locomotion over rough terrains. And that was what I was very interested in, because I thought, there are a lot of robot demos are in a lab on a flat ground, very controlled, and sort of studying what it would take to take robots out from the lab and into the real world was very fascinating to me. So I worked about 2 years on state estimation for hybrid systems. So I worked on state estimation for hybrid systems during my master's. And that was basically the focus there, was to understand how we can track a system state that goes through a hybrid event. So like you're swinging your leg and then you touch the ground, and there is like a discontinuous large change due to impact. So how can we track in our estimation that kind of a discontinuous event? And most of the current estimation techniques cannot handle that, which you don't see them in autonomous driving or other applications that are becoming mainstream, but it's definitely an ended question of how can we perform dynamic motions and be able to track our velocity states closely. And then after that, there was an opportunity to join Zebra as part of sort of a startup project that they were doing in warehouse robotics. So that was pretty interesting to me, and I wanted to sort of, with the new knowledge and the algorithm understanding that I developed through my master's, sort of get that industry experience. So I joined Zebra as I think the second person on that team, and was there until last week. So
it was a startup, right?
Yeah, it was basically a startup project within a big company. And within a year and a half, we were able to go from nothing to, having pilots with major logistic companies and major warehousing companies that are pretty well known.
Like autonomous mobile robots?
It was mostly on we weren't making autonomous robots. It was more about coordination algorithms for multi-agent navigation.
Okay.
So basically the software stack that goes on top of multiple robots coordinating the fleet. We can call it fleet management software. And then, after that, so I think it kind of lined up nicely, because by the time I left, the project got into more incremental improvement phases of it. So, which is not really what I'm interested in. I early stage development and sort of research focused jobs. And then came back for my PhD at CMU. And the good thing is that now my research is very inspired from what I've done in the industry. So I focus on one thing I realized in industry is that a lot of current approaches, either you have to build a very controlled environment for the robot to deploy thousands of them, like what Amazon is doing, or even if we have a robot with flexible dynamics, that like a quadruped or something, we don't have those deployed at scale. So it's if you look at the quadrant of scale and task complexity, here we have Roomba, simple robot, moderate scale. Amazon Robotics is all the way at the top, but very simple robots. And then Boston Dynamics has very advanced robots, but not at scale. So, and that comes from sort of how can we expand into that quadrant and see what it takes to bring dynamic complexity into scale, which I think is where a lot of value can sort of be unlocked. So that's the theme of my PhD so far.
What is your big vision? Do you want to stay in academia or go back to industry?
My big vision is I want to have my own company. So
that's
it's
good.
kind of somewhere in between.
That's
I guess.
Inspiring. Yeah, please talk a little bit about that.
Yeah, I mean, I sort of been trying a lot of different things, and it never quite I always thought that, okay, this is the answer. And I tried, I was like, it's interesting, but it's not the answer. So I tried early stage startups, bigger company, academia, I think pretty much everything I can think of. And at the end of the day, I realized that, okay, I want to work on very challenging problems. I need the flexibility and freedom to be able to do those, which academia offers that. But at the same time, I don't want to end sort of the journey with a paper. I'm very interested in, okay, how can we bring these results? There's a lot of research in robotics that stays in the labs. And although those bring sort of understanding, there is also quite a bit of opportunity in how can we connect these to a real application. Like every paper I read starts with, this is where a method like this can be used for these applications, but I never see it actually used in those applications. Like we talk about search and rescue, but I haven't seen any multi-agent search and rescue application of a robot in real world that can actually do it. So that's sort of been my inspiration. And the reason I decided to do the PhD was it gives me that freedom and flexibility to explore those questions and really narrow in on what I want to do. I think I found a rough area right now, but I need to get on a very narrow question that I say, okay, this is the question that this business is going to answer, and this is what the value proposition is, which I guess is the journey that.
I'm sure you will be successful in that.
Thank you.
So about your posts on LinkedIn, how to become the deep dive post, how to become a robotics engineer. What made you decide to write the post on how to become a robotics engineer, and what gaps you saw they were important to fill?
Yeah, great question. So when I was actually done with my master's in this journey that I just went over, CMU is particularly obviously a hub for robotics. So it's very clear, like, what are the subfields, what are the skills. But even at CMU, I never felt that coming out, I was like, okay, how am I supposed to prepare myself for an industry job? Like, what does it mean to be a roboticist? What skills do I need to focus on? It seems like there's an ocean of information out there. And there is a million subfields that one can sort of focus on, but it's unclear how you should actually approach it. And there is a lot of resources on how to do interview prep for software engineering roles, but I think there is a fundamental difference, and even companies sometimes mix the two. Mm-hmm. So after sort of going through this 1.5 year journey, working in industry and having experience before that, I realized that, okay, probably I think a lot of other questions, but people have the same questions. And I actually wasn't sure. I kind of wrote it because I thought it would be useful. And then I wrote the first one. And then like the next day, more than 100 people messaged me on LinkedIn. I was like, okay, apparently a lot of people have the same questions. So yeah, that's not a question anymore. So then after that, I sort of structured it in 10 different posts. And then my advisor actually, in a subsequent meeting we had after I wrote all 10, he was like, you know what, I think you should make this a permanent format, because people have to hunt down like in your profile where this post was. And I was like, okay, let me just like make it a Medium post now. Mm-hmm. And yeah, I mean, it was the first time that I really felt like, okay, something I wrote has a lot of audience. And I mean, people normally don't see the work in the background. I've been writing and posting for 2.5 years consistently. And it's really not like I just decided to write something and it kind of, people found it interesting. So there was a lot of like, okay, are the things that I think important, are these actually important to other people, or is it just what I'm thinking? So yeah, that was sort of my motivation. And then now I have a lot of ideas on next sort of series that are currently in progress.
Great news. One check-up for you for these posts. They're really good and informative. As I observed the reactions and people's engagements, I realized that you are right. And they were something that people had needed for so long, but had never been able to talk about or ask for. So You did a really great job, and congratulations. I read your article that is a combination of all these posts, as you mentioned, and you put it in Medium. I would like you to discuss them with our viewers today. What are the steps and skills for becoming a good robotics engineers? And just talk about the orders in which you like.
Sure, absolutely. So I guess the first thing is when I was going through this journey, and I'm still going, I always thought that the more I know, the better. I always wanted to know more. And although that's a great sort of thing to be after, at times it can also be distracting, because how much you know isn't really that important. What's really important is how much of what you know can you apply. And so that's sort of what I've learned. So I think in order to become a robotics engineer, the first step is to mentally just prepare yourself that you're never going to know it all. There's so many concentrations, subfields. Even within a field, there are like a million research questions and subfields that people are working on. So that's the first thing, like just mentally understanding that I'm never going to be an expert in perception and motion planning and control at the same time. No one is. And even people that are leading teams of multidisciplinary people, they have a general understanding of a few of these areas, but they still only are an expert in one. So that's I think really key. Just before even starting to get into it, just understand that okay, there is so much, and you're not expected or should really think about learning it all. The other step after like getting into that sort of mindset is one, focusing on foundations first. I think oftentimes people start like going to some algorithm in motion planning without really understanding graph theory, without really understanding how to write a good C++ code. And it's basically small building blocks that'll get you there. So before really getting into some, fancy names out there or fancy papers, I think what's really important is to focus on foundations. And these foundations, one is C++ Python programming. I think I discussed that in the article as well. Being able to turn your thoughts and ideas into code quickly and understand how software development works, how you should debug, how you should test your code. These little things often people overlook, like, oh, testing the code is easy. But when you actually try to do it, it's actually a very complicated process. So starting with C++ Python, and then on the math side, you need some tools depending on what area you want to concentrate in. In general, for most concentrations in robotics, you need to have an understanding of optimization theory. So just knowing how to formulate optimization problems, how to implement them, and how to debug them, because a lot of times it just won't work. So having a strong linear algebra, optimization theory, and statistics probability on the math side. So C++ Python programming, and then having a good math foundation, I think is really every roboticist needs to have these. And if you skip these and go to like just implementing some package, it'll bite you later, because in interviews or even in the actual job, you're expected to debug solutions that don't work out of the box, or develop your own solutions. That's exactly when having this in-depth understanding can help you. And then, so after these kinematics and dynamics.
Question here. So most programs like mechanical engineering program, like the one that I came from, they weren't really focusing on programming languages. So what if person is in these programs and he or she wants to be a robotics engineer, but her program doesn't offer these courses? What he or she should do?
Yeah. So, I mean, in general, more and more programs are adding sort of CS courses to their curriculum. So there are two ways. One is you can always take advantage of your electives. So if you have electives, you get to choose what you want to choose. So I personally focused mine on more programming heavy and computer science courses. So that's one option. The other option is that there is, abundance of courses and information out there. And I think the key thing here is to not just do the course and then do another course and then another one, is to get the basics, but then start building something, right? So if I, for example, want to test my C++ knowledge, I can take a basic course to learn the syntax or some data structure, but then come up with your own problem. Say, okay, I want to, for example, search a graph and then find the shortest path, right? Once you've studied it, once you've taken a course in it, implement it on your own. And this can be a very frustrating and tedious process, but it's exactly during that time that you develop that skill and the intuition. And I think the most amount of learning I've personally had was through hours of debugging something and struggling. Because it's really easy to sort of trick your mind into knowing something after you've listened to someone explaining it to you. But there is a big difference between actually doing it versus thinking that you know how to do it. So that's how I would think is a good approach there. So where were we? Okay, so C++ and Python, optimization theory, statistics and probability basics, and linear algebra. So this is like sort of your math plus your programming. And then the next step is kinematics and dynamics of multi-body systems. And this is something that most graduate programs nowadays have a course in robotics, an introductory course. They cover these. But there's also, I think I referenced the Northwestern University course on Coursera in my article. That's also a very good one, visually and really clear, explaining these concepts. And it's really important.
The textbook is one of the best in for learning robotics. I've read that
definitely.
textbook, and it's one of the best. Yep.
Definitely. Very clear and without too much jargon. I think it's great. And basically, the reason why kinematics and dynamics is very important is because no matter what you do, at the end of the day, you're dealing with a multi-body system. Whether you're trying to do control or motion planning or perception, you still need to be able to do coordinate transformations, generate equations of motion. Maybe some fields like control need a heavier understanding of dynamics than like perception, for example. But I think every roboticist needs to have an understanding of these concepts. So I think with this, you sort of have most of the tools. Another thing I think is important is once you have these foundations covered is simulation. Being comfortable working with at least one simulator. And that this doesn't mean you have to like develop your own simulation features. This could be, as simple as just knowing how to load your, for example, CAD model in Gazebo, as an example, how to set up boundary conditions, how to configure a simulation, how to run it, how to get the results, and just, the whole end-to-end process of if I have some scenario that I want to test, being able to actually demonstrate that and end-to-end go through the process. Again, simulation can be its own sort of world. There are people spending their lifetime developing simulators, but just the basic understanding that sort of gets you to testing your logic and your solution. And then from there, I think this is what I call the foundation. So once you have these, you should be, I think one thing I also missed is ROS. ROS is also another foundational skill that's very important. And again, with ROS, it's very easy to get overwhelmed quickly because there is so much, just even getting used to the vocabulary of ROS, to me, took like 6 months at least. Because there's so many concepts, and I thought that, okay, I have to start reading all of them and then understand all of them. Whereas in reality, you just need to take it very incremental steps. Like, okay, can I just build a node first? And then can I just, publish to a topic? Can I build another node that subscribes to that topic? Very, very incremental, small steps. If you do it consistently, then you have a wonderful project at the end. So it definitely doesn't come from sitting down and reading a bunch of documentation endlessly. It's more about learning something small, doing something small, and then keep on sort of repeating this cycle.
So you're basically talking about like project-based learning, doing small projects and learning as a matter of doing that project.
Exactly. And the question I get most of the times is, what project should we do? And I think that's also another thing that each individual should figure out by themselves, because the process of also coming up with something that is doable is a learning experience. A lot of times you say, okay, I want to do this, but then actually when you try, you're like, oh, there are these limitations. So then you have to narrow the scope a little bit. Mm-hmm. So I think it's really a process that's sort of self-driven, that, you have to decide. And this is where the dreaming part happens. Okay, I want to do this. So let me do some research, see, is it feasible or is it too big of a scope? And then if not, let's narrow the scope and find this chunk that I can actually execute on. And it doesn't have to be this magical project at the beginning. Even like moving a motor through ROS is a good first sort of step. And then from there, once you get used to this sort of framework of how ROS works, what are topics, what are nodes, what is like the execution model, how does the communication work, then you start building more and more complex projects. I remember when I first started my first project, I had no idea how ROS worked. And it's still up to this day, after working so much, still confusing at times. So it's really not about like knowing it all or getting to a point where it's like always in process. Even today, I get stuck on something for days. And I just have to like work through it, just like a beginner again. So it really has nothing to do with how many years. It gets easier, the basics, but there's still challenges because you do harder and harder projects. And then, so once you have these foundations sort of covered, then from that point on, you can decide what sort of concentration you want to develop a deeper understanding in. And right now, I think there are 5 concentrations. Again, it's dynamically changing, but I think, currently and hopefully for the next few years, there's only these 5. So 1 is motion planning, 2 is control, 3 perception, sensor fusion or localization, and then software infrastructure. And so you don't have to immediately decide, I think, which one you want to do. I think it takes time and exposure and sampling from different things to understand what is it that you truly like. And again, it's different thinking that you like something versus actually doing it and knowing that you like it. During my undergrad, I was interested in aerodynamics, but then I was never exposed to mechatronics and robotics and what it would mean to build an intelligent system. So a lot of times you just don't know. And then, like, I never knew, even during my master's, I took a motion planning course in my last semester. And I basically, I just spent 100% of my time in that class. I liked it so much that it became sort of this passion. And that sort of led to, even continuing it in industry and then doing a PhD in that. So I was doing state estimation work for like 2 years. So it's always sort of an evolving process. Mm-hmm. And I think what's important is just for beginners is to just start sampling different things, just a little bit of every one of these, and see what is it that you truly like. What type of problems you like solving? Are you into robot behavior? Are you into controlling, tracking a certain behavior? Do you like working with images or videos? Computer vision, or do you just like pure code? You just like to code. So then, software infrastructure may be a good sort of focus to develop. And so I think it definitely takes a couple of years really to hone in on something. And even then, after a few years, you might, transition to something different. But I think once you've sort of figured out roughly what you want to focus on, then the next step from there is to start reading a lot of literature around that area. So I think in industry, reading literature is very underappreciated. It's more like an academic thing. But to me, it always helps a lot with intuition. Mm-hmm. A lot of times, even though if I don't know how to solve a problem, but if I've been reading a lot around that area, naturally ideas start to form, in my head. And it's a weird process to describe, but it kind of naturally, the more you read and learn about different solutions, you naturally start thinking about the right approaches. And so this is something that you don't develop by writing code or like doing math. It's just through reading literature consistently. So I think what I suggest is dedicating some time weekly to just read literature. For me, it's like Friday mornings. It's like 2-3 hours. I just go through, filter literature, and then pick 2-3 papers and then really do a deep dive, the core papers that contribute a lot. And so that's how I try to develop that habit of being up to date and thinking about the solutions. And then once you have sort of a familiarity with that literature, then you can dive deeper into implementing algorithms, right? So you have your C++, your Python skills down, and then you can write a generic program, but the real skill is, can you take an algorithm from a paper and implement it? And can you find the limitations of that algorithm after you've implemented it? I think that's really the key here.
That's that literature thing. That's a really good pointer to read other people's work, because sometimes I look at different kind of robotics work, and it's like people are just copying each other, because it's exactly what you're talking about, because they don't know about other people's work, and they think that their ideas are original, so they're developing it without knowing that somebody else is doing that. So sometimes they are exactly the same. Right. Do you agree with this?
Yeah, I mean, especially in my field, like I know nowadays, because, and also it's like some of it is good, some of it is bad. I think copying for the sake of adding to your publication record, I think that's a really toxic and bad culture in academia. I don't agree with it at all. But I think oftentimes it's easy to criticize a paper by reading it. And I think one efficient way to actually criticize a method is if you actually implement it and then you run it, then you start seeing the limitations and then start nudging it from different angles. See, is this failing here? Is this failing there? Like, for example, one very concrete example, when I was working at this job in industry, I was reviewing a paper on a certain algorithm, and it had many citations. Like it was insane, thousands. And then I was like, okay, let me just implement this. It should be working fine. And then when you actually implement it and run it on the robot, you realize, okay, these are the issues that come up that are not addressed here, potential research areas. So I think copying to get to the boundary of that knowledge and then going, a step beyond that, I think that's great. But I agree that right now there is a lot of copying just for the sake of like one
Maybe
more
it's not copying. Sometimes people do something and they think that their idea is original, but because, as you said, they haven't studied the literature, they don't know that somebody else is doing that. And I find that nowadays, no idea is original. Somebody else is in this world is thinking about that.
Yeah, right. And I think I agree with that. But I think also, I mean, academia defines this originality as this, like, you have to come up with this grand theory that beats everything before. I think the definition of contribution doesn't have to be something like that. Mm-hmm. If I show a method that already exists, but haven't been shown on hardware, if I show it on hardware, to me, that's a contribution. Mm-hmm. Because there is a million challenges on just getting something from simulation to hardware. So it doesn't necessarily, I think, have to be this grand thing that breaks the world. Even if it's an already existing method, but with practical considerations implemented. That could be, I think, a novelty there. Because there is a gap, right? You have a paper describes a method, and then you have an application industry, and this paper doesn't solve that application. So whoever can close this gap, to me, that's also a novel contribution. So I hope that in the next few years, robotics research goes more towards practicality, and that we have a million problems out there that can be solved with these methods. But the focus needs to be on solutions rather than robots. I think Roboticists always try to build robots, but in the real world, people need solutions. So we have a bunch of startups that are trying to sell one-off robots, and then companies think about it and they're like, I have to buy this robot and then buy that other robot. I need a solution that solves my problem. So that's, I think, one key point that I learned in industry is that whatever you're building, it has to be solving the problem end to end. You can't be just selling the piece of a solution. And that's, I think, why there's a lot of struggle, even for companies at the caliber of Boston Dynamics, to commercialize the robots. Because at the end of the day, it doesn't really matter what the robot does. It's all about cost to value ratio. So if the businesses cannot justify the cost of a robot over the value it provides, then they simply won't buy it.
Yeah, they're looking for the return on investment for the
exactly.
Industry.
Yeah, which is difficult. If a robot is $50,000, exactly. Why would I buy a $50,000? Like, what kind of an application should it do to justify that? Like, people say, oh, cleaning. I can hire someone for $10, $15 an hour to do cleaning. So spending $50,000 for a robot that can do the replacement of that job is not a
mention the yearly maintenance cost.
Yeah. And then, which is the reason why a company like Intuitive, for example, is valued over 100 billion, because the complexity of the task they're replacing has a lot of value. So, helping with the quality of a surgery, that has a very high price tag. So then you can sell one robot for that kind of evaluation. So I think, yeah, it's really about either you're replacing a simple task in scale, which is like picking in warehouse, or you replace a smaller scale task that is very complex. So the sweet spot is how can you replace complex tasks at scale, which is sort of the dream. Yeah. So I think once you have sort of the C++, Python down, the skills, and then you are at a point where you roughly understand the literature in your area of focus. Could be motion planning, could be control. Then from that point on, I think the next step is like a big jump. But I think that's really the skill in industry that's lacking a lot, and companies die to hire for, is being able to implement algorithms, even from existing literature, and get it to work, test it reliably, identify areas of improvement, and have that depth of understanding to say, okay, I think this paper solves this problem well. I implemented it, I tested it, and I'm able to deploy it, and support any future, upcoming bugs or issues, improvements that may be required. So I think that's really the key to securing a high-level industry role, is being able to implement solutions end to end. Companies want someone to take ownership of the process: literature review, solution identification, implementation, testing, deployment, support. And if you can do this end to end, you have a place anywhere in any company, I think. And so that's what I would say is, after covering the foundations and the literature, is the next big jump. And again, through doing projects, there are lots of repositories out there, like I mentioned an example, C++ robotics. There's like on GitHub, it has a very clean and nice implementation of well-known planning algorithms for someone who's interested in planning. Again, you don't want to sort of end there. You want to get inspiration, but then let's say the problem is solving it on a wheeled vehicle. Try implementing the same algorithm on a quadcopter with quadcopter dynamics, or try doing it with like a Segway dynamics, some different platform that requires you to think a little bit and reason through some complexity. And I think that's a process, obviously can take some time, but I think by that time you are at a proficiency level to be able to target industry roles and really become a true roboticist who can, go from literature review all the way to a complete solution deployed on hardware. And again, it's a lot of little pieces in between that obviously I don't have the time to go for here, but it's just recognizing that it's a long journey. So you have to really make sure that it's something that you want to do. You're not doing it just because it's the hot thing right now, or it's because, everybody is hiring for it. Although those are not bad reasons, but it takes more than that to fight with the problem for hours. It takes really passion for what you're doing and loving those struggles along the way, because there's going to be a lot of them, and it's not easy at all. So, and the more the higher you go, the more difficult it gets, because then the pool of people you're competing with, they're now more and more competent, right? So nowadays, like, interviewing for senior level roboticists is like, you have to really know your stuff end to end. So yeah, that's what I would say is roughly the roadmap. From my experience, other people may have other approaches, but that's something that has worked for me. And yeah, I think I have full description of it in much more detail in the 2 articles. But yeah.
So you mentioned that you categorize these jobs as motion planning engineer, control software, and those kind of things. What if somebody's passion is not in demand? So if you're passionate about motion planning, but there is not much demand. So, because I know that a lot of companies are now looking for software developers for robotic systems, especially university graduates. So what if somebody's passion is not in demand by companies?
Yeah, I mean, so I mean, it depends. So if you're really passionate about something, I mean, I within robotics, I personally think that all of these are right now in demand and will be for the foreseeable future, just because the industry has really just kicked off 2 years ago, to be quite honest, at scale. It's been really 2 years where you have this abundance of VC investments and startups and really scaling up. So I don't think that's going to be an issue for specifically these roles. But I think it's a process where you evolve, right? So you may be interested in motion planning, but then maybe motion planning in particular isn't in demand, but its intersection with perception is now in demand, right? I know even in our research lab, for example, we look into problems where you know how to plan for a rigid body, but what if you're with your camera, you're seeing in front of you and you try to select good footholds for the robot to step? So, that's now an intersection of planning and vision. So I think one interesting approach there is to look at what other areas neighboring to your area have intersections. And normally you find a lot of interesting applications and also a lot of demand. Like right now, I think most of the robotics work is becoming very focused at those intersections, right? Okay. How do we see better to move, not just seeing better for the sake of it? How can we move better to see? And sort of how these connections can be leveraged in a way that improves the overall system. So I think that's an approach that I would personally take. And also, it really comes and goes in waves. I mean, if we go 10 years back, robotics was a dead field. Even if you go 5 years back, it still was relatively dead. I mean, if you look at Boston Dynamics, they've been around for a long time. And no other company really showed anything up until very recently. So it really comes and goes in waves. But I think it never really goes out of sort of norm per se. It just evolves. We had automotive engineers. Now we have autonomous driving. And then from autonomous driving, we probably go to, having your own little airplane that you just travel in uncontrolled airspace. So I think it's like constantly an evolution. For robots, for a while, it was how can we get this one robot to pick an object? Now it's about, okay, we can do that well, but can we do this reliably with 50 robots? And can we just let it run 24/7 without having to, have support engineers on site constantly, watching the system. So I think it's definitely the challenges 5 years ago aren't the challenges today, but they're new challenges. And so which is where the passion is important, because if you're passionate, you constantly push yourself and you constantly enter those new areas and grow further.
So yeah, I agree with you. From after this COVID thing, because people didn't want to interact with each other, these autonomous systems are more popular nowadays, and new solutions pop up every day. One question came to my mind, that a lot of robotics job seekers, in the job description, they see that nowadays, especially after this COVID pandemic, a lot of companies are requiring skills like machine learning, artificial intelligence, deep learning algorithms for robotics graduates. So some people find it challenging because it wasn't something that was covered in robotics programs. At least I didn't have it as a course when I was a graduate student. And it's totally challenging for these people to be in these jobs. So what do you suggest in this area?
Yeah, so I think obviously it's like so I'll answer it in two different ways. One is that all of these deep learning algorithms, they're just replacing a part of the stack that was already working before.
I agree with you.
So that's I think it's a very important thing to recognize. I think oftentimes it's over glamorized. At the end of the day, a neural network is a universal function approximation. That's all it is. So, and in robots, we normally map from one input to one output. We have some control algorithms to do that. You can replace that with a neural net. It comes with its own problems. So I don't think fundamentally it changes anything with your understanding of how a robotic system is supposed to work and is constructed. However, I think it helps to understand where are the areas where the traditional methodologies lack, and how does it have the potential to fill in those gaps? I think that's the level you're expected to know. And I think if you have a deep understanding of the traditional methods, you naturally know the gaps. For example, if you're into model-based control, you know that as soon as your dynamics are deviating from the model, your controller isn't good enough. So that's one area where you can say, okay, can I learn my dynamics now through some function approximation, through some neural net, and replace it that way? So I think it's really not about becoming experts at training neural nets and managing ML pipelines and things. That's not an expectation for robotics engineers. You're expected to know first where the traditional methods are lacking, and then through doing research and reviewing literature within still your own area. Like right now, there are papers solving motion planning with reinforcement learning, right? So it's not scattered again. You're still focusing on your own area, but now you say, okay, let me see if there is a learning approach that solves this, and what do they argue is the advantage, right? Or does that make sense? Can I criticize this approach and say that no, model-based is still better, or traditional is still better? So that's, I think, is really what's expected. Another thing I think is to recognize that still today, more than 95% of systems in industry rely on those traditional methods. Yeah, and I think there's this misunderstanding that everything is now shifted to learning. Learning has shown a great promise, both in robotics and also outside, but there's still a lot of issues with guarantees, robustness, generalizability that requires years of research to get to a point where we can just run a neural net and just call it a day. So I think that's
been around for at least 50 years. I know neural networks, machine learning have been around at least for 50 years, but it became a fad, especially in these 2 years. That everybody, and each paper that I saw on IEEE robotics, some sort of learning algorithm is used in implementing.
Yeah, and I think I don't want to be oblivious to it. I think there's definitely, there are certain things in robotics we do here with heuristics that are just kind of we're forcing a solution, and it seems like something like a neural net or reinforcement learning would make sense. Like, for example, selecting the robot footholds given a terrain map. That's, you have a lot of sensory information, and with heuristics, it's very difficult, especially if the ground isn't flat. It's very difficult to come up with good foothold candidates. So those type of things, I can see a learning approach sort of fitting in nicely. However, I think it's also important to recognize that there is a lot of limitations with these approaches in reality, in practice. They all work nicely in PyTorch, but the moment you run them on the robot, you run into noisy signals, generalizability issues, and then you're very biased towards what you were training this network on. So there is a lot of challenges that come up with it. And so I think it's important to have this objective look and understand what it is, what it's good for, and what are its limitations, rather than just saying, oh, this is the future, like this, everything is going to be learning, which may or may not be, but I don't think that's the right approach. And then the other thing is, this is kind of towards companies, is that I think it's becoming a norm where every company just adding machine learning to a job description, regardless of what it is nowadays.
Exactly.
Like some job titles I read, and I'm like, so you want me to know MPC LQR, and then also RRT planner, and then also deep learn? Like, these are very, very different things, and there's a lot of depth here. So that's also something. You don't have to be checking every box on a job description to be qualified. I never checked more than half of them, to be honest, for any job. And I was still fine interviewing and getting positions and stuff. So I think that for beginners, they think that if they don't check all of these boxes, that they don't have a chance, but it's really not true. The companies do this as a strategy to get the best, to get the people that are, skilled and know a lot. But at the end of the day, I don't think anyone expects you to know motion planning and also be an expert in deep learning and then something else.
Yeah. Thank you so much, Ardalan, for your good pointers. So I want to ask you about a day in the life of a robotics engineer. Maybe some people are interested to know about what is it like to be a robotics engineer?
Yeah, it varies a lot from day to day. Some days just meeting marathons. Some days heavy on development. In general, that's how I structure my days, and I think it's different. But in general, I'm a morning person, so from 8 a.m. to noon-ish, I just completely sort of block all the distractions and focus on development. And so normally the morning time, lots of reading, coding, debugging, running simulations, things like that. And then I sort of try to push my meetings to afternoon time because I get a little bit sleepy after lunch. So that's where I think is my less efficient and productive time. So, and it depends. When I was at the company, you can have technical discussions, algorithm meetings, a new problem came up in production, discussing solution approaches. And then a follow-up discussion to that. Okay, once we've nailed on the solution, let's now architect the code and this particular module that solves the problem. So lots of technical meetings. Some also just organizational meetings. Like in university, we have lab meetings and meetings you just have to go to. And then one-on-one advisor, more focused meetings and technical meetings like that. And then depends on which stage of the project you're in. Some part of your time can also be spent on the hardware. So right now, I normally twice a week go on site to work with the hardware and test things for two reasons. One is that's also a skill. So if I don't do it for like 2 months, then I go there like a beginner, don't know how to turn on the robot and like do the basic things that I used to do. So that's one reason, but also just incrementally testing things, because a lot of times things work in simulation and then we run it on the robot and it completely fails. So understanding why, I think, is very important there. yeah, so if it's an early stage project, mostly software focused, you may not have that until you're sort of into the later stages. And yeah, I mean, people think that I work a lot, but I really just try to not work on Saturdays and Sundays. I genuinely try to set that time aside and I suggest all other passionate people trying to get into the field to do the same. The time you spend resting and relaxing your mind adds to your productivity. It doesn't extract from it. So I think it's really easy to get into this like loop of, okay, I need to write more code, do more. But after a long time, you sort of get exhausted, and then you start getting diminishing return from your.
You're also very active in social media, like LinkedIn. You write a lot, and that's a very good.
Yeah, I normally do those after work hours. So like at nighttime, normally dedicate like an hour or so every night to do sort of either, writing on LinkedIn or social media, other things. Because I just think it's an exciting field, and I think general public should know more about it. Mm-hmm. And not only people that go to CMU or MIT or Stanford has to know about this field. There's a lot of talent out there that for any reason aren't in any of these programs, and so they shouldn't be just left out and having to all figure it out by themselves. So I think that's also important to me, and I try to do it as much as I can, although it gets challenging at times. But
thank you so much, Ardalan. What is your final take-home advice for robotics learners?
Yeah, if I want to say one takeaway that I had in the past few years is to stop comparing yourself to other people when you're learning.
Oh, yes.
And I think, I've been in this situation. I think every single grad student or undergrad student has been in the situation. Learning is a very non-linear process, and it's like some people learn fast initially, but then they stop learning. Some people learn slow initially, but then they explode, and it varies a lot. So I think it makes no sense to try to compare where you are, how fast you're learning, or how good you are, whatever metric you're using to make that comparison. I think if you just focus on doing something you love, and if it happens to be robotics, and you do that consistently, you will get incrementally better every day. And you will get either the job or whatever opportunity that you deserve ultimately. I truly believe in that. You just should focus on the process of getting there and not thinking about who else is there or this job opening or I failed at this job. I have failed at many job interviews, failed many school applications, but it kind of at the end all worked out because I really just loved the field and I still do. And I just wanted to work in it for however long possible. So that's really my one advice is just focus on your own learning. Do not compare yourself with other people and just be consistent with it. A little bit every day goes a long way. You don't need to do too much at once. A little bit every day, after a year, you're working on a quadruped doing something crazy. So it's those little efforts, step by step, consistently that ends up in big results. Which is why a program like a PhD is 4 years. If it was like a quick, get it done, it would have been 6 months. But there's a reason why it's that long, because it takes that long to build something meaningful. So that's my advice. And yeah, I hope this has been a useful session for everybody.
Yeah, it sure is. Thank you so much, Ardalan. I really enjoyed talking to you, and I'm sure that the viewers would also enjoy this conversation. Thank you so much for your time. And I want to let you go because you have lots of things to do. Have a nice day.
Thank you very much. It's been my pleasure, and hopefully we can do this more again.
Thanks everyone for watching. I hope this discussion was helpful to you and you became familiar with tips and skills needed to become a good robotics engineer. Be sure to follow Ardalan's LinkedIn for more posts about robotics. And also be sure to become a part of the Mecharithm family. Have a nice day. and God bless.